Today we're going to review logarithms. We're going to need to know how to use logarithms for some of our calculations in kinetics and also for calculations when we start looking at equilibria and in particular pH. Let's start with just the basic idea of what logarithms are. A logarithm, base 10, as you see here, is called a common logarithm of some argument a, or just the log of a. If a is a number that is a power of 10, then the log of 10 raised to a power of x is just simply equal to x. In these examples, you see how that works. You have the log of 100, and 100 is a power of 10. It's 10 to the second power. And the log is just simply returns the power on the 10. So we have log of 10 raised to the second power is just simply 2. Here we have the log of 0.00001, which is just simply the log of 10 raised to the negative fifth power, and that just returns the power on the 10, negative 5. Log of 1 is equal to the log of 10 raised to the 0 power, and that returns a 0. However, log of 0 is undefined. And the reason why it's undefined is that there is no number that you can raise 10 to a power of that will give you 0. Here is an example of the natural logarithm. The natural logarithm is the log of some argument a, base e, right there. And the ln represents log base e. And it's called the natural log of a. And for some of you, you may have forgotten exactly what e is. E is very much like pi in that it represents an irrational number. E is approximately equal to 2.718. And if a is a number that is a power of e, analogous to the way if a is a number that is a power of 10 for our previous examples, then the natural log of e raised to the x power is just simply x. And again, we have the similar examples as from the last slide. The natural log of e raised to the second power gives us a 2. And then the natural log of e raised to the negative fifth power is negative 5. And again, the natural log of 1 is the natural log of e raised to the 0 power, which is 0. Now in science, our arguments of the log are not that clean. They are not these clean powers of 10 or clean powers of e. You must use the log or the natural log buttons on your calculator to get the answers. So why don't you try plugging in the log base 10 of 4.57 and make sure that you get the following number to just check to make sure that you know how to use that function on your calculator. And again, do the same thing with the natural log of 0.023. Make sure you get this number too, because it's very important when you're doing your homework or you're taking an exam that you are familiar enough with your calculator to get the correct numbers with it. Now, there are some things that you need to know regarding logs. Well, first of all, the argument of the log, the base 10, or the natural log function is always a positive number. The numbers that you put in here must be positive. You cannot take the log of a negative number. Now, if the argument of the log function is greater than 1, the answer is a positive number. We can see that in this example. The argument is 4.57, and that is a number that's greater than 1. And you see the log of 4.57 returns a positive value for an answer. However, if the argument of the log is less than 1, then the answer is a negative number. And that can be seen in this example. So the natural log of 0.023, which is a number less than 1, gives us a negative number, negative 3.77, etc. And you will never see the log base 10 and the natural log functions mixed together in the same algebraic expression. However, there is a conversion between the two. So if you need to, for any reason, convert between natural log and log base 10, you just simply use this conversion and it works like a charm. Now we need to know how to use significant figures with logarithms. And here are the rules. If a number has x number of significant figures, then when you take the logarithm of that number, you round the answer to x number of decimal places. Here's an example. We have the natural log of 3.46, and that equals 1.2412, etc., etc. So we have 3 decimal places for the argument. That means we have 3 significant figures in the argument, which means that we need to round our answer to 3 decimal places. So our answer for the natural log of 3.46 is equal to 1.241, rounded to 3 decimal places. Then, when you raise 10 or e to the x power, you count the number of decimal places of x, and the number of decimal places becomes the number of significant figures you must have in your answer. So essentially, you do the reverse. If x has a certain number of decimal places, you type in x into your calculator, press the e to the x button, and then you round that to the number. That number that you get needs to have the same number of significant figures as the number of decimal places in this x. And continuing on in this example, okay, we took the log of 3.46 and we rounded it to 1.241. Now, an excellent check of how these two rules complement each other is to see what happens when we raise e by a power of 1.241, which is the rounded result of taking the natural log of 3.46. So we take this number, e to the 1.241 equals 3.459070807. We have 3 decimal places here, which means we have to round our answer to 3 significant figures, and we get our number back. There are a number of mathematical operations for logarithms that you may have learned before that you will kind of need to remember how to use in order to solve some of the problems in kinetics and in when we start studying equilibria. First of all, and these are analogous to each other, so I'll just kind of focus on the log base 10. So you're taking the log of 2 numbers multiplied together. Well, that equals the log of one number plus the log of the other number. And if you were to take the log of 2 numbers divided one from the other, then that equals the log of the numerator minus the log of the denominator. If you're taking the log of some number x raised to the yth power, you can take that y and move it out to the very front so that you get y times the log of x. Now, if you are taking the log of a number that is it's the yth root of a number, then that is just simply, if we were to rewrite this in terms of some sort of a power, then we are taking the log of x raised to the 1 over yth power, and like in the above, you can take that power and move it out to the front, so you have 1 over y times log x. And then finally, as we've seen before, the log of 10 raised to the x power is equal to x, and of course the natural log of e raised to the x power is x. And then 10 raised to the log of x is also equal to x, and e raised to the natural log of x is equal to x. And let's look at some examples of how we can use these rules. In this first example, we are taking the log of 5.0 times 10 to the 6th, scientific notation perhaps, and I can, using this rule, the top rule here, I can split this up. I have the log of 5.0 plus the log of 10 to the 6th power. And using my significant figures rules, I have two significant figures here in my argument, and when I take the log, my answer needs to have 2 decimal places. And there you go, 0.70. And in this part, I have log of 10 to the 6th power, and using this rule here, I just simply wind up with 6 as my answer, and then I add them up. The next example is log of 154 divided by 25. And what I chose to do is to separate the numerator and the denominator. So I have the log of 154 minus the log of the denominator 25, which equals 2.188, and I have 3 decimal places here because I have 3 significant figures in my argument. And then my other term is 0.140. I have 2 decimal places in my answer because I have 2 significant figures in the argument of the log. And then I perform my subtraction, and in my subtraction I get 0.788, but I am not done, because when you do a subtraction you need to consider which of the numbers has the fewest number of decimal places and round to that number of decimal places. This one has 2 decimal places, so I need to round this number to 2 decimal places. The next one, I have log of this number, 5.46 times 10 to the negative 3rd, raised to the 6th power. I chose to use this rule here and bring my y out to the front. So my y in this case is 6, so I brought 6 out to the front, so now I have 6 times log of 5.46 times 10 to the negative 5th, and that equals 6 times negative 2.263. Again, I have 3 decimal places in my answer because I have 3 significant figures in my argument. And here's my final answer. My final answer has 4 significant figures. And then finally, I am taking the 4th root of 4.35 and taking the log of that. And I used this rule where I can just move this 1/4 out to the front. So I'm multiplying 1/4 to log of 4.35. 3 significant figures, and my answer has 3 decimal places. This is the homework that I would like you to do for next time, and you will hand this in. I did provide you the answers so that you can check your answers, but I want to make sure that you know how to perform these operations and round them to the right number of significant figures. Thank you, and take care.